Just a minute. Clean? Oh, okay. Oh, sorry.
Okay, you already recorded?
Okay. Okay, good morning. We are in the day 2 of the training sessions in the context of Open Data Science Europe workshop. And this was a R session, and now I will speak about Python. But of course, in the same context. So I will explain how we are mainly how we are optimizing our computing process, and regarding to the raster data set and how we are processing and organize all these raster layers that we are putting available in the web viewer. So, and I will present about mainly 2 examples. So accessing local data that we prepared previously in the Virtual box, and I will access also the through cloud optimized GeoTIFF. So it's in the end of this presentation, we will have a short use case for cloud optimized GeoTIFF. So it's a kind of invitation and introduction for the afternoon session that will be specifically about cloud optimized GeoTIFF in Python. So before to present the example, so I would like to introduce about the specific about parallel problems and how we can understand it. So there is a specific subfield or category of problems called embarrassingly parallel. So in the most part of rasters processing are classified as this type of problem. And considering that, I will discuss and present what are the possibilities to optimize this raster processing workflow, and mainly how we are doing it in the context of the project. And I will discuss about these 2 implementations, BLAS and LAPACK. So for sure, if you work with data science, no matter in R or in Python, you are using it on the low-level libraries. So these are C libraries that are used for the most part of raster processing and mathematical operations. So, and I will show one of the benchmarks that we prepared and how we cannot optimize your processing workflow without change anything in your code. And later, so in the hands-on part, in the demonstration, the practical part, I will show how to optimize a temporal array reduction and a numerical operation, a calculation of NDVI. And the last part of the presentation, it's really present our production workflow and how we are using like our tiling system to split the process across different servers and write in the output, and later put all this data together, generating one single cloud optimized GeoTIFF. So first, it's good to introduce this type of problem. So in the computer science field, you have this embarrassingly parallel problem. So this name, it's for me, it's a bit confusing. But if you think in the embarrassingly, it means that you can split the problem in really independent parts that will not communicate at all with each other. So it's really embarrassing. So you can really embarrassing all the problem, this one specific problem, and split it. And if you think, for example, in a remote sensing data, it's actually in a raster data processing, it's actually it. So you can have one pixel, split it, send for different processing units, servers, CPU cores, and you can do a sort of operation, and later you can have the result. So this the most part of problems in the related with the raster data and computation problems are like that. But you have this nearly embarrassingly parallel. So in the context of the remote sensing, we are dealing with like thousands and thousands of pixels. So you need to send the data to some processing unit, and after you need to get the data back, the result of the processing. So there is this second level of classification, nearly embarrassingly parallel, that it's related with these two at the end and the beginning and the end of the processing. So you need to send the data, split it in different servers or different processing units, do some operation, and collect the result of the end of the processing. So it's more called like nearly embarrassing parallel, but you don't have any communication between the process. So after send the data, the processing unit can do all the work without communicate each other. And as I say, this is the most part of raster processing. So here is example. So if you think this is an image of 5 kilometer of spatial resolution, and for this image we have one big time series. So this is a AVHRR data set, and you can perform several operations on it. So you can do trend analysis, you can try to identify breakpoints, things like that. And if you think in all these pixels that we are seeing here, it's about 96 millions of pixels. And because we are dealing with the embarrassingly parallel problem, if you have a giant and like huge computer with 96 million of cores, hypothetically you can send each pixel for this processing, and you can get the result of the process instantly. So this is one example that can show to us that it's really like it's not easy, but it's more straightforward, define like ways to split the processing and to optimize it. And of course, you can buy more hardware or get more servers, but you need to be aware that in the remote sensing field related with raster data processing, you always need to send this data, and so the data access, it's also a bottleneck and could be an issue. So considering that, we can say that these are mainly the possibilities to optimize your raster processing workflow. So increase the number of cores, and that one, okay, you can buy more servers, but if you have, I don't know, 100 servers reading from the same place, so you will create a bottleneck to access the data. So you need to also improve the data transfer speed. So there are hardware solutions to do it. You can improve your network speed. You can create like connections between the servers, like directly without pass through like a suite network. But this is more related with hardware. Considering the software part, so the processing code, of course, you can develop new algorithms or functions, or you can use this drop-in replacement. So what is it? So you can mainly use the same code that you are having, that you already implement in Python, in R. You can just replace like a part of low-level library, and use like a more optimized function that will do the hard work like for you. So it's a kind of new algorithm or new function, but for your use case, it doesn't have any impact. So that's one type of it's one way to optimize it. And the other way, it's really you need to do the hard work and re-implement your code. But of course, the most part of the frameworks that we have available to do it, they try to minimize your re-implementation effort. So because of course, it's always better just do a drop-in, replace, change some specific library, and you optimize your processing, improve your speed. So, and in this training session, I will show some examples of how to do it. So in our notebook in Python, but these two implementations, they are really like available for different language, so including R. So if you think you have this BLAS, it's a basic linear algebra subprogram. So it's written in Python C, and plus just in C, sorry. So, and you can see these are basically like low-level functions that will do some basic vector and matrix operations. So, and if you think this is a C library, so everything on top of it, at the end, we will use it. So for sure, you are using these libraries in your workflow in some way, because I assume that every one that it's watching this and participating of this training session process at some point raster data. And you have this other library like linear algebra package. So it's written Fortran 90, and it can manage and solve linear equations, least square solutions of linear system and different types. It's more specific, but some of temporal analysis use it behind of the hoof. So if you think, and what is interesting about these libraries, today they are kind of a standard. So if you think in these methods, so you can have the same method, the same signature, the same parameters, and you can just replace the code. So it's actually like a standard that define this method and the parameters, and you can just change the way that these operations are really performed. So you can do a drop in replacement really quick, just changing, for example, with different implementations. So considering these two standards and these two libraries, we have several implementations, but mainly, and some of these implementations were discontinued, but now these four are mainly like the mainstream implementations of the BLAS and LAPACK. So you have the Intel MKL. It's not an open source solution, but Intel provides it's free, and of course it works better with Intel. It works actually specifically, and it was designed specifically for Intel processors. You have the OpenBLAS. That's an open source implementation. It's optimized also. But of course, they don't have the same budget of Intel. So in the most part of the benchmark, MKL, it's the best one. So AMD now it's creating more. It's creating one implementation for BLAS and other for LAPACK. So it's actually two libraries, but MKL do the both implementation in one single package. And for the AMD, it's really like it's not really unstable, but it's difficult to set up, so it's not as straightforward as MKL, but AMD it's trying to provide a good implementation also. And you have like implementation of these libraries to run in GPU. So and NVIDIA it's providing it and giving support. So it's a nice implementation also, and you can use if you have a GPU and just do a regular, for example, Numpy operation or a regular matrix operation in R using your GPU, just replacing these libraries.
In principle, it's more cost effective, right? It's way more cheaper to compute. The cost of chips are lower.
Yeah, if you think like per processing unit, yes, but GPU it's more tricky because if you buy like a good CPU processor, you use the memory of the workstation. But GPU has your own memory, so actually you need an additional step to send the data from the computer memory to the GPU memory, and you need to manage it. And sometimes you actually you have CUDA, and that it's a library to do it, but these packages and this library they have problems with the memory. So if you are dealing with like large objects in memory, probably you need to deal yourself with this type of problem. But it's a nice solution, and we are slowly trying to use it more. And this is a benchmark that we prepared, and by the way, it's executed in R, so we run it in R. And mainly what we implemented a harmonization approach, including a get filling operation and like a trend analysis for this AV-HRR data for the whole world. It's a 5 kilometer data. But what it's interesting is we use exactly the same code. So we changed nothing in our code, and we just replaced the 3 implementations: MKL, OpenBlast, and Bliss and libflame from MND. So you can see that the Bliss and libflame, the stop didn't finish for some bug in the middle of the process. But if you compare MKL and OpenBlast, so MKL it's 3 times faster, and we used it just changing like the R environment to access different implementations of these of these libraries. And so considering it, what we will do now is actually use the data that we prepared in the context of the project and optimize and reduce the computation time to considering different implementations of Numpy. So mainly we will use Bottleneck, NumExpr, and Numba, and at the end I will show how we are doing our tiling system, our tiling processing, but it's more like for production work. For the exercise, we will compare these 3 implementations with like a regular implementation of Numpy. So, and in this, I was talking about this libflame and libpack, and it's important to emphasize that our environment, it's already set up to use MKL. And for example, if you download for R, I think if you download the Microsoft version, they already provide it with MKL. So maybe you already use MKL, and the speed that you have, it's using this. And so in the context of this training session, we are using MKL, and we will improve it, but using a drop-in replacement inside of Python. So we will replace like the engine to do the processing in the Numpy. We will replace with other implementations that relies, for example, in C and C++. So before to enter in the practical part, I would like to check if there is any question about this first introduction and more like conceptual background. Let me check here in the chat. Okay. Okay, so I will open the VirtualBox here.
This thing you showed that the one is 3 times less efficient. I mean, that also depends with what you have also depends what you compare, right? Or is it universal? Always.
No, it depends. In our case, we were using like a specific raster processing, and there are like in that case there were a lot of code is written in R, but it was the same code. We just replaced the last part, like the low level function. But for sure, it's for other type of processing could change. But my suggestion, it's important to, there is no like silver bullet. You need to do some type of benchmark specifically for your workflow. And that's why we did for our workflow, because we are dealing with this trend analysis and processing this data and like in the data cube formats. But maybe if you are more using other type of spatial process, I don't know, like a sort of segmentation that deals more with the space and needs to work like with big matrix, not a specific one pixel in the time, but like more in the space using different pixels across the X and Y dimension. Maybe it's different. So because I don't know, it will use different functions in this lab. So it's difficult to create.
You always benchmark.
Yeah.
Any process you have, you pick up the libraries you use, benchmark.
Yeah, my suggestion, it's just a drop-in replacement. So you can just use the same code and change the library in a low-level implementation and do it. So we will do it here in Python, but again, these implementations are could be used in different language. So that's the main advantage. And yeah, it's important to do a benchmark, understand where is the for what library it's best for your use application. So the first thing I would like to do is I will clean here. So let's first I will back here. So if you open a terminal, you at this point you already know that we have this ODSE workdir, and inside of this folder we have the code, and we already have the repository for the training sessions. So the first thing, you need to do a pull and get the most updated code, and I already did it. So, and for your case, you should receive some more content, because we are updating this repo and adding the content for the training sessions. And at the end of all these training sessions, we will keep the repository with the presentations also, and everything will be here. So first thing, it's get the update your code, and later I will just keep it open, and I will open again this is my presentation inside the VirtualBox, and I will to open the Jupyter Lab. You can do it here, so it will execute the Jupyter Lab, and if it's open it the first time, if it's your first time, you will see this, and you can enter in the same folder that you got the new code. Open here, Python training sessions, and we will execute this notebook. So high performance computing in Python. And the first thing that I will do here, it's and I don't need to see it, so actually it's here. So there is a way to, I guess, Control B. Okay. So, okay. And so mainly in this training session, we will use these functions. So bottleneck, it's a collection of NumPy fast functions written in C, and it's important all this bottleneck and all these other implementations, they manage with the not a number values. And if you remember the other training sessions in Python, when you read the data and you have like a no data or like a pixel that we are not mapping, like in the ocean water, it reads as not a number in Python. So when you perform, for example, operation across the time, and if you organize the data in a data cube structure, and if you have like a no data, you need to ignore it. Otherwise, you will see like a no data, and your all computation will be compromised. So it's important. All the operations that we will show here, they ignore this no data to not affect your calculation. So, and if you click here, you can see all these libraries, but I will not do it. And you have this NumPy expression. It's more like a expression evaluator, and it optimizes the memory usage, and you can define your calculation like in NumPy using different mathematical expressions. So we'll use it to calculate NDVI. And you have also Numba. Numba, it's the for me, it's the most robust framework considering what we have here. It's a just-in-time Python compiler. So you can use it, and you are using this framework, you are able to translate like a function that you write in Python. You can translate to C and just writing Python, and it will perform the operation like in a compiled code. So it's a fast way to optimize your workflow. But you need to change your functions. Like, so you need to, if you have like an operation to do like a NDVI, you need to create a new function and implement it. But in the most part of the case it's doable. But there is a lot of other functionalities. It's a really a robust framework, and here we will use just to specifically to present two concepts of this library, like the drop-in replacement. So it's a kind of we will use the array reduction. So we will optimize like a median calculation across different years, and we will also use the vectorize function that it's actually, it will create a C++ function just in time. So what you need to do first is set up the main Python modules and libraries. So you can see here that we are using the NumPy. I will clean up the output here. So restart the kernel, clean the output. So yeah, the first thing, it's really load the modules and the libraries. And you can see we are just loading the NumPy and the pathlib to deal with the file paths. And we are using three functions from EUMap. So find files, read and save rasters. So to read rasters in parallel and load it in memory and put in a NumPy array, like in a data cubic structure. And we use the plotter just to see the result. And in this virtual box, you have two tiles available. One is for Greece, another is for Netherlands, specifically for Wageningen. And here it's just we are set up. We will set two variables to with the data, and we will use this raster dir variable to access the data input for the demonstration. So first, we will access the Landsat data. So as I presented yesterday, this is a temporal data set. So you have several files that represent, each file represent one season and 1 year. So we have for each year we have 4 files, and in the file name you can see the time frame used to produce it. And in this data we produce it for all the Landsat bands and for all and for each season we calculated 3 percentiles: the median, the percentile 25, and the percentile 75. So we use it a lot in the Python training sessions, but here we will use one of the spectral bands to calculate our array reduction. But before to read the data, I would like to explain what is this array reduction. So it's a approach where you have like a multi-dimensional array. So because here we are dealing with 3-dimensional array. So you have like space, 2 dimensions, and 1 dimension is time. So it's a data cube. But in Numpy, you can have multiple dimensions, so 10 dimensions, it doesn't matter. If you load, for example, all the Landsat data, you have 4 dimensions because you have the spectral dimensions, so all the spectral bands, you have the temporal dimensions and 2 dimensions for the space. So then you can put everything in one single array and do the same operations that we are doing here. So mainly array reduction, it's a way to reduce one of these dimensions considering a specific operation. So here it's a book example just to explain. So you can see you have an input array with 2 by 2, and we have these numbers here. And mainly if we perform like a maximum operation in the x0, the first x, we will have like as output a new array, but now with 1 dimension less. So, and this concept you can apply for any kind of raster data. You just need to find a way to put this data together. And in the EU map, we are providing the functions to do it specifically for temporal data. So if when you find the files and you create the file names and put it like in a list, it will read the file. The function will read the file in the temporal order because it's the same order that we have in the file name. So we will do it now, and you can see here that I will execute the code. I'm providing a function to show some informations about it, and you can see this is actually we used this function a lot yesterday, but you have this raster dir, and I will execute it in an individual cell. And oh, it's better if I just get the first. So, and you can see in the raster dir, the folder that we defined on the beginning of the training session, we are just looking for red Landsat percentile 5th. And you can see that we have this object here. It has like 84 files, and I will just print in the first 5, and you can see it start from the first date that we have, and considering the product that we prepared, it's the winter for 2000, and it's sorted. So these are inside of this function. This is a UMap function that we developed. We sort the files, and you just need to send the files to the read raster. And now you have like a data structure, like a multidimensional array with 1000 by 1000. So it's the size of our tiles, and 84 times. So here we have all the Landsat red band load in memory. And you can see that we are using the floating 32. So, and if you check these values, I think I do it here in the, for some reason this, yes. So I will do it here just to show the values. And you can see that we wrote, these files were saved, like, I will just get the first image. And you can see that these files were saved as byte, but to when you load it, you need to have it in float. So we use more memory, but the most part of these libraries, they are optimized for float. And the other point is you just in the Python, you can only use like not a number as a value inside of array in a floating structures. So in the floating data type. So it's, we optimize the file. So this is a file where we are saving byte. So the values here will be between 0 and 255. But to deal with that in memory and to optimize the processing in Python, you need to convert to float, and mainly for two reasons, because it will be optimized for the most part of these libraries, and you need to manage this not a number, and it's mainly a no data. So, and this function here, the read raster, it's actually it's reading the data, putting it together, and as all these files, they have like a metadata informing the no data. It's already replaced the no data value that in this case here it's 0. It's already replacing it for not a number. So it managed it for you, this function.
It's a 320 megabyte RAM at the moment.
Exactly.
And, but how big was it on the disk?
Yeah, we can check. Yeah, we need to check it. We actually need to check each file separately, but let's get one, just one.
Also just some file storage.
Yes. So I will just get the name here. This one. So you have this multiplied by, I will just, because each file probably it will be different because it depends of the values, but it will be something like that.
About 6 times.
Yes. Yes, and but one thing that's important, when you save the file as GeoTIFF, you have the compression. So you have the compression algorithm that will reduce the file size, and you have the data type that use less space. Byte use just 8 bits. So here in the floating 13.2, we are using much more bytes also. So these are the two reasons. So, and yeah, this function you can use to see the data type, and I'm just plotting the size of the array here. And so what we will do now, all our benchmark calculations here, and all, then I will use this time IT. So you can see it's like a command specific from Jupyter, and you can define the number of repetitions. So that is really important, because when you do a benchmark, you actually need to execute it multiple times. Otherwise, it depends of. And in this case, even my computer, it's doing other things here, because there are other softwares that are working. So you will have a better estimation and a more reliable estimation if you use multiple repetitions. So what I'm doing here, I'm doing this 5 repetitions, and I will use this Numpy and not a number median. and I will reduce the temporal dimension. So mainly I'm calculating here a median across all the seasons and all the years. So it's a long-term median of the Landsat red band. And to do it, I just need to execute, and I will see the time. And remember, this time it's taking a while because it executes 5 times. And the output, we will see the average of the computation time and the standard deviation considering the 5 executions. No, because Numpy doesn't run it in parallel automatically. This is the regular implementation of Numpy. We can see it here. That's a good point. So if you put here, and let's execute again, you can see that it's just 1 core. And mainly they have some reasons to do it, because depending of the way that you split the process, you will create a new process, you need to send the data, and after you need to process it, and you need to aggregate again. So at some point it's not worth, but other libraries did it. So for example, the library that we will see here, they implemented it, but it's just 1 core. And again, this is just the regular implementation of Numpy. And now we will do the same thing, but using the bottleneck. But the bottleneck, it's a good example of drop-in replacement. So it's the same signature. So it's the same method, and I'm sending the same data and the same parameters. I will do the same operation, but I just need to change the model name. And if I do it, and let's see, yeah, it's about 4 times faster. In this case, it just used 1 core. So you can see. And mainly they use it like more optimized functions to do the same operation here. And yeah, it's 4 times faster. One thing that I would like to show is,
just a second. So this second one, the bottleneck, doesn't parallelize.
Nope. Then it's 4 times faster. Maybe they did some algorithm optimization inside of each of these functions. This bottleneck, it's not fully compatible with Numpy, but for example, maybe they found a way to implement a median calculation using some heuristics that it's better.
Have it still on parallel, then you can go even faster.
Exactly.
Okay.
Exactly. But one thing that this is nice to share. So we use it a lot in the project. We use this floating 16. And if you think the float 16, it's the same properties of the floating 32. So you can have no data, but of course you are using 16 bits. So it's 2 times small, considering you use 2 times less memory. And you can see here it's 160. But if you perform the same operation using, now you can see I just changed it, and the read raster, our function manage it. So now it's just a floating 16. And if I change it and I just execute, the computation time will be bigger. So it depends of the data format that you are dealing, and float 16, it's not like it's not the most optimized format. Frankly, I don't know why and what are the reasons behind of it, but you can see it's much more slow, this function. So and we discovered it during the project. Some of the calculations that I were doing inside of the EU map used this float 16, and it's 6 seconds now. So if you deal, for example, with GPU processing, you will have the same problem. So to really optimize your processing workflow, you need to manage this data format and you need to understand it. There are some limitations, but in general, float 16, it is a limited format, and but of course it uses less memory. So if you want to optimize, you need to use more memory and process your data faster. It's what we are seeing here in the context of these libraries. And I will execute again. So yeah, and it's the same code. I'm just changing the data format here. And so what is nice, and you can see this is not parallelized, but and here I'm doing a median calculation, but this is 4 times faster. And if you use, like, I don't know, processing the whole continental Europe as we are doing, so it's a remarkable improvement. But what it's really important, you need to be aware and you need to check if the data is the same, but maybe, I don't know, they could reduce some precision in the calculation. And if you check with this array equal, you will see that they are exactly the same. So we used 2 different functions that produce exactly the same result. So I'm using like the right function to do it, array equal. And you can see that it's exactly the same value for all the pixels that we are generating here, and the result, and it's 4 times faster. But you can use other function, and we will do it now, and we'll do with this Numba package. But the example that we have now, it's a drop-in replacement. So it's just a matter to change the model that you are importing, and you will have a faster implementation. But with Numba, it doesn't work like that. You really need to do some work. It's not hard working, but you need to re-implement part of your workflow. And as I said, it's a more complex library, and here we will use this JIT decoration. So it's a just-in-time compiler, and you have different options here. So and you need to put it on your signature method, and you need to define that it's a non-Python implementation, and here you can use the parallelization also. We will do it. So, and as I said, there are multiple ways to optimize your processing workflow with Numba. And here, but Numba works in a different way and doesn't provide this array, this axis argument. So, and if you can check it here, so all the functions compatible with NumPy, you have it here. And so they try to use the same signature, but it's actually, you can see that here, it's just only the first argument. So we are using the same function of NumPy, but for their specific reasons, they didn't implement like this X reducer. So informing that we will reduce and we will calculate the median across the temporal domain. So you need to manage it in the implementation. And here I'm just showing that to deal with that, what we will do, now we have a 3-dimensional array. So we have like 1000 by 1084 temporal, 84 dates. But as Numba just work with a 2-dimensional array, it's just a matter to change the structure of your data. So what I'm doing here, I'm just doing a reshape, keeping the same, the last dimensions here, and I'm putting together all the pixels in this space. So I think this is pretty common for R, So because it's how the some of the packages, yes, they use like that. But for NumPy, we actually work with the data in three-dimensional structure. But here it's just a matter to do this reshape and keep all the temporal dimension intact, but put together all the pixels in the space. And now
the second one, you would be able to do any spatial filter or something. Because now it's just a vector, right?
That's a good point. You could process each image individually, but so that would be an option, but not like one single chunk of data. Yeah, you are right. If you in this operation, you have this limitation because of the way that some of NumPy operations were implemented. So what we will do now, to use Numba, mainly you can you need to define this JIT, just-in-time compiler, and you can see that I'm creating like a reduce function, and I have the last dimension here and the output dimension, and here I just presented the shape that we will put in Numba. But here I'm doing the reshape. So I'm changing the data to three-dimensional to two-dimensional structure and keeping the last dimension intact. And I'm sending it to Numba. And now inside of Numba, I need to create a new array. So this X, it will be a new array with the same size of the input data. And I need to use this P range. So in Python, this range, it's a pretty common function to iterate over the data. And this P range, it's an optimized range that will parallelize the workflow for you. And here we are creating a P range across this 1 million pixels. So, and this I here will be actually like one of these each lines. So, and now you can just call that not a number median and do the same operation and put in this X and return the result. So till here, we will send it to Numba, it will be processed and we will receive the result. But of course, we would like to have it in a three-dimensional array as we are doing for the other libraries. So I'm just reshape again the output. So, and let's put now the terminal. And if you execute it, you can see now that it's using all the cores, and now we have half seconds. So, but it's not like a lot of work of coding, but we need to re-implement our approach and do some changes. But there is no free meal. We need to do it to improve the result, or we just can use like a drop-in replacement as we are doing here and improve just 4 times. So here is 8 times faster than the original implementation. And again, you need to compare. So it's exactly the same result. I'm not losing anything in this processing. So it's really an improvement in the performance. And here I'm just using the plotter function to see the result. Of course, I already compared all the values, so visually it's the same thing. And this is the final summary. So, and just to explain, it's more like related with this time IT. Each time that I executed it, I defined this -O. So it will be the output of this benchmark will be saved in this object. So at the end, I can generate like just a visualization of it, putting all the results together. So here I'm getting the average and the standard deviation of the 5 executions for all these 3 libraries. And definitely Numba, it's way better. And it's produced exactly the same result. And so this is a array reduction operation. And just to emphasize, here we are using like the median function, but you have support for all these implementations. So it's some of bottleneck doesn't have all, but you need to check specifically all these libraries separately, but you can perform several operations. And maybe for some operations, it will be faster. I don't know, maximum, probably it's more simple to optimize than a median function. Like a percentile, it's more difficult to optimize. So this is not like again, a golden rule that always will be faster, but for sure, if you use Numba or bottleneck, you should see some improvement considering the original implementation of NumPy. So I will show now the numeric operation, and the numeric operation it's a bit different. So the array reduction, mainly we have the input array, and we will reduce one of dimensions. So it's mandatory that the output will produce less data than input, because we are reducing the data. So here we are reducing all the temporal dimensions in this exercise to the one single dimension and removing this time dimension, just calculating the median. In the numeric operation, it's mainly like some type of calculation that will receive the same input and generate the same input. So the same output, considering the shape, not the values. But it's more to perform some operations. So it's perfect to calculate, for example, spectral index. So we have like two images, and each image, of course, one image for red and other image for near, and we will generate the NDVI. So of course we are receiving two inputs, but each input has the same structure, the same shape, the same dimension of the output. And here it's just an example. So we have this in data and two inputs here. So it's just a two-dimensional array in NumPy. And I'm just performing like a multiplying the values, and you can see the result. So we have two input shapes with the same dimensions, and the output shapes will be also the same dimension. So now we need to read the data, and as here we will calculate like an NDVI across this data. We need to use two bands. So we need to use the red and the near. So, and what I will do, I will get all the files here. So I'm finding the files, the read, the red and the near, but I will just read 40 images. So the first 10 years. And it's mainly because I want to keep the same amount of run of the last exercise. So, but you can play with that and you process the whole time series. And you can see here it's the shape. So again, it's the same concept. We are reading the data. The files will be returned in a sorted way, and we use this to read the data in a temporal way because it's the same order of the file name. And here we are reading two data. So, and now we have the red and the near data. So it's a pretty simple NDVI calculation. So who works with this satellite images and environmental monitoring know this index. And here I will do just performing like regular operations, because with NumPy I can do it. So it's compatible. So it works like one. It works like for one variable. And here it's an array, a three-dimensional array, and it will be performed for the same way. So I'm just calculating the NDVI here. And let's see how is our RAM. Okay. Took a while because it is a 5 times repetition. And you can see here standard deviation between all these 5 repetitions. And for the number, so here for bottleneck, I didn't see any implementation or any function to help with that. So in this case, just Numba provided, and with Numba we will use this vectorized decorator. So mainly what we will do, if you think here, for example, we are doing like, we are calculating like a subtract operation, a division over an array, but the way that I write the code, it's the same way if it's just one value. So this type of flexibility, it's mainly provided by this Numpy universal function. So it's more like a paradigm that it implements different ways to access this arrays structure and provide it in a high level usage. So you can perform some operations easily across multiple and multidimensional data sets, arrays. But what Numba do here is when you use this vectorized decorator, so you can check more the documentation here, it will implement the same structure, so the same paradigm about this Numpy universal function in C. And what is nice is you can keep the same way that you are writing, and it will manage everything for you. So it's a just-in-time compilation, and it will optimize it, the process. But to use this vectorize, you need to define like what is the input value and the output. So it's just it. So here we are defining that we are using floating 32 because at the end this function will be converted to a C function, and these data types are really important if you do it in C. And you can see the return here. So index exactly the same code. In this case, it's almost a dropping replacement. So, and you can execute, and you can see that it's half time fast. So it's not a real like it's a. Of course, it's an improvement, but not like 5 times faster as the other one. But it's pretty straightforward. So you can use to optimize it. And of course, here you can perform any kind of operation. So, and you have support for different mathematical operations and different calculations, considering this vectorized decorator. And so, and of course, it's important to compare if the data is exactly the same and check if we are not losing anything. And yes, it's exactly the same. So we are really optimizing it without changing the output. And in this context, the last library is this Numprex. It's difficult to say, but it's more like a Numpy expression calculator. And this is more like it's a nice library, and it's really simple. You have the main method is this evaluation method, and you have all these available functions like cosine and arctang2 and things like that. All these functions are supported, and you can write your calculation as a expression. So, and you can see this is actually a string, and you are here, it's a calculation for the NDVI, and I'm defining the parameters in a second object. So I'm defining like NDVR data. It will be remapped to near, and rad data, it will be remapped to rad. And you can see that it's just define the expression, send the parameters. Here you can send like a constant. I don't know, maybe if you put some constant in, if you will calculate, for example, AVI2, you have some constant and you can define it here or inside of the expression. It doesn't matter actually. And here you are sending this expression, the parameters, and this optimization. It's more like it's a default value, this aggressive, but I just inform it there because you have these three, actually are two options, moderate and aggressive. And I'm not sure, but I think it's related with the memory usage. So, and if you execute it, so it runs also in parallel, and you can see it's a bit less, or I think here it's almost the same time from the Numba. And you need to check if we are producing exactly the same date, and you can actually compare the results now and see the performance. Let me check the chat. So yeah, we have one question. So are the general rules for deciding whenever to use Numpa, or Numpa just the max speed while Numpa reduce the memory usage? No, I think that's a good question. I think that it depends of your workflow. I think the difficult part here, it's really to integrate these libraries in your processing workflow. For sure, it's a kind of work. For bottleneck, for example, it's just a matter to change the model, but maybe there are some functions that are not available in the bottleneck. So I think the first point, it's really like it's related with the implementation cost, and you need to, it depends of each application. But in general, I assume that Numba, it's probably the most robust framework here, and of course it will require more implementation work. But for me, it's a trade-off. It's a balance between the effort to re-implement part of your workflow and the gain in speed, for example. Maybe you just use bottleneck and change just the model importation, and you will improve a lot, but it's not necessary to change anything. So that's works for you. And I think that's more like kind of the general rule here. And of course, Numba, it's the learning curve, it will be bigger for sure, because with Numpy, this expression evaluator, it's just like one method, so it's really easy. And with bottleneck, it's just a matter to change the model. So Numba, it's the best option, I assume here, but it will require more implementation effort, and the learning curve, it will be like more difficult. And okay, so, and now what we can do? So yeah, we processed 4 NDVI images, right? And you can check them here. This is just a function that we already used in the past training session yesterday. So you can see the NDVI values for 1 year, so the 4 seasons. But I think it's a good idea, save the images, right? So you processed it, we did that exercise, but we are generating like a new data. So, and I like to show this rasters, save rasters, because it's really handy. So if you see here, I will just open it here. So this is our NDVI output. So it's a NumPy array, and mainly I will send this NumPy array to the save rasters, and I will send a list with all the files that I want to save. So if you think we will generate 40 files here, and each file needs to have a name because we are putting all these temporal bands in separate files because it's easy to access and to get specifically one time if you want. But to save it, I need to save as raster. And if you think in a raster format, you have different parameters, projection, like pixel size and things like that. So to deal with that, we are sending like one base raster. So it's just one example of file. And I will just get it here. And I want to show the first, I'm generating like a list of files where the data will be here. And now I can send like this list. And of course, the list needs to have the same amount of files of the dimensions that I have in my last, the size of the last dimension in my NumPy array. And here it's actually a file that exists. This file needs to be exist because inside of the function, we will get all the parameters like projection system and everything and save it. And this function, it's fully optimized and you can do it here and it will, now it's using 4 workers. It's a kind of default value, but you can save, I don't know, using 10, 20. If you use 40, maybe it doesn't make much sense because you will have a bottleneck with your disk. But here we saved all the 40 files. And now let's open it in QuantGIS. So and here you can see the files. And one thing that it's important, this file is, if you remember, this is a byte format. So because we optimized it, so the values are between 0 and 255. But here we calculated an NDVI and we didn't rescale the value. So I'm sending, you can send like some additional parameters. So I sending to the save raster that I want to write like a format, like a floating 32. Otherwise I will truncate my data because it will put all the values just like one single constant because I can't represent like floating points in byte. So yeah, if you open here, you can see, and this is the NDVI that I calculated, and probably here I used the same node data, so all the values that are equal to 0, they were classified as node data. So that's a problem, but we can inform in the save raster, we can define the node data output. So yeah, this is mainly the output of calculation that we defined, and you can change the node data here if you want. So now, till now we did everything just for one tile. So for me, it's a good way to start because you have like a pilot area, you have like a small data set, and you can really tune and find what is the best approach to do it. So this is part of the optimization process. The other part, it's really like production work. So now, for example, we can use all these implementations, or actually we use just one, the better one, and we will like produce it, but like in a production way, and process several tiles at once. So in parallel, and we can, for example, split it in different servers. So the point here is we optimize it for one single tile, but of course, depending on your study area, you have much more tiles. And in our case, in the Open Data Science Europe context, we have more than 7,000 tiles. So what I will show here, you can see that if you have just one single tile, it's like that. But if I would like to load all the tiles in the context of the project, I would use 26 gigabytes, just one date. But if I would like to use, like process as I'm doing here, imagine I will put the whole Europe, all the pixels, 84 dates, like 20 years, all these seasons that we are processing. So it's a lot of RAM. So if you need like almost more than half terabyte, and some computers have it, but for example, the problem here, you need to be aware that all this data is compressed and it's saved in a storage unit. So it will be a long time just to put everything in memory and later put back in the disk. So you have like a data access problem here that it's actually unavoidable. But the best way to deal with that, it's just really splitting the process. And of course, if you use more servers, you need to be aware that it's important to provide a fast way to access this data through the network. Because if you use multiple servers, they will access one single place. So, and it's important be aware of that. So, and the best option is use this cloud object service. So you have like the S3 service option, and Google has one also, and you can use it to process. But of course, if the data is in their infrastructure, you need to have the servers there also, and you need to put it to run there, and in some cases that's okay. But if you have your own infrastructure, you need to have if your servers are running, for example, in-house, you can use an open source implementation for this S3 called Min.io. So what I will do now, I just have 15 minutes. Let me see here. So yeah, I would like first to show it here. So this is our current processing workflow. So to process Europe, we are sending, so we have more than 7,000 tiles, and we are sending like just the bounding box. So each of these tiles, they have like one bounding box, like a window object in the raster. So we are sending this bounding box for these different servers. So here in this example, we are using 4 servers. And this servers has the Python, the Docker, it's the same environment. But the most important, these servers will access like data storage, but it will access through S3. Actually, here we are accessing all the files as accessing directly to HTTP connection. So it's not actually a S3 because you don't need any type of permission and credential to access that. But and of course, you need to provide a good and reliable network connection here. So all these servers are in the same switch network, and you can access it. And there are options to do it. You can use optical fiber. So for in-house processing, there are multiple possibilities. And later, so we send just the bounding box, we read all the data that it's necessary, we do the calculation, we save back here, so we send all the data to this SSD and NAS. So, and to save, we actually need to use the S3 protocol, and later we use the GDAL, our good friend, to generate, like first we generate a virtual raster. So it doesn't matter how much tiles you have, GDAL will manage with that. We generated like files with more than 100,000 tiles, so it's not a problem. And GDAL will create this build VRT. So as it called it, it's a virtual mosaic that will point for the data. And using this virtual GDAL VRT, we do like a GDAL translate and generate all the cloud optimized geotiffs. And in this, so this is how, for example, we generated the NDVI data that we that the red band that we accessed now. And I will do just a short demonstration here. So to access now the data through the cloud optimized geotiff and our S3 service. So you can see here, I have a URL, and this URL is actually pointing for NDVI that we processed for the whole Europe, and this is a specific date. And this is nice, so I can just pass this URL, Raster.io will open it. I'm using Raster.io just to see like the parameters. So I can see here the whole image, everything. And what I will do, so in the EU map, we developed this tiling process. So all this mechanism to send, for example, a specific one window for multiple CPU cores, we are managing it here inside of the tiling process. And we have three functions. One to process one single tile, other to process all the tiles, and other to process just a range of tiles. And here I'm just getting one specific tile. So what it's important, I'm sending like an HTTP URL. It will be received here by this function. And you can see in this function, I can receive the window that it's actually linked with this tile ID. And this is just a sequential ID. And here, as I didn't send any parameter, I could send a different tiling system. It will use automatically the tiling system from the Open Data Science Europe. So with the more than 7,000 tiles. So here I'm getting the tiles from the cloud. The method will just pick up this tile with this sequential ID. And with this tile, I'm sending to the read raster, the same function that we used. I'm sending like the URL. I'm reading just one. I can read in parallel, but here I'm just using one job. But more important, I'm using the spatial window. So here I'm just reading from a cloud optimized geotiff, a specific part of my data. And the result that I want to receive, it's just a byte format. And I'm using the plot function. So, and I can see the result here. And of course, you can play with this parameter. I don't know, maybe you can try to see other region of Europe and it will do the same thing. Here we can see some stripes because of the Landsat data, and you can check other regions. So this is totally working through network. But you can process, like, you can see multiple tiles. So here it's just the same function, but now I'm passing a range. I will pass like a range of 3, and I can see 3 different tiles. And this is the location of the window. But what I will do now, actually, I will get, considering this URL, I already have the red and the near band there, and I will get this URL and I will generate, like, here I have the raster files. So I'm using the raster files just to replace, and I will show you just some example. So this is a remote URL, and I'm accessing this remote URL, and now I will calculate an NDVI accessing directly from the cloud optimized geotiff, but I will do it for 3 tiles. So, and you can see it's the same approach. The read raster, I'm getting it specifically for window. To optimize the processing, we need to have the floating 32. And here I will use the Numpy Express. So it's just, I will call this evaluation function and I will have the result here.
How many of these read rasters can be done on that server? Tested, can you do like 500?
No, I never tested. There is some limitation because, but for example, here I'm using 16 workers. because there are two levels of parallelization. The first one you can see here, the 3 tiles are being processed in parallel, and each of these tiles I will read using 4 cores. So, but I think maybe the limitation in their side will be more for specific for one IP, but I don't know. Because if you have multiple IPs accessing it, they need to provide some type of scalability. So here we did the same thing, but now with real data accessing a specific part of the word, and we processed it and generated it internally here. And I will just open it to show, and as we process it, like.
And then you can probably, when you run it, you can see how you download the data, right? You have to download some, maybe 100 megabytes or how much.
Here we download the full resolution, so it's the same size that we estimated that time. So yeah, it was.
Now when you run this, you downloaded almost 50 megabytes.
Yes.
Right.
Yes, 50 megabytes exactly. So, and here I will just open the data that we produced. So I created this, and this is other thing that it's nice. So for example, the save raster, I'm using the save raster, it will create all the folders for you. So you just need to define the output, and I define it here, like NDVI production. And so I'm just saving all the data. And here we have the 3 tiles, and you can open it in OneGIS. Yes. And you can use now a GDAL VRT and put these tiles together and generated one single file. It's actually, this is our current workflow. And the last thing is, yeah, these are the commands to generate it. And yes, you can see that I changed the format. Okay, I would like just to explain this structure. So you can see that you can play with this file structure here. And of course, you can send it later for a S3 server. But what I did, I just keep the same file name that I want to see. So here it's the NDVI. So I'm accessing the red and the near band. I'm generating the NDVI specifically for this date. So when I enter here, it's a nice structure, has all these tiles that I will generate. So more than 7,000 files in a single folder. So I can just use like this command here, this GDAL build VRT, just pointing to use all the files here inside. So it doesn't matter if I have 3 files or 7,000. So it will work the same way, and you can replicate this command in the same way. And yeah, that's all that I have to show to you. Let's see if I have questions here in the chat. No? Okay, we have 3 more minutes to discussion.
Tutorial is in the GitLab.
Yep.
You can find it. And there is a bit of choice bar, or
There are more 2, bottleneck, and the other it's Numpy Express.
Okay. So the one I did in R, I just used parallel. And this one, I think I don't know if it's something faster, but the code I made is fully scalable also. You can put also different functions here. Run for time series data.
Yeah.
So it would be interesting to compare R, the one I made for R, Python, to do a benchmark.
Yeah. Hardware and same.
But your estimate is now you work in R and in Python, and your estimate is for processing rasters. Python is faster.
Yeah, I think it's because, for example, you can use the regular functions like in R, in Python, and you can just change like the the MKL, so that there is no change in the code here. But I think these functions are really the frameworks that I presented here. They, especially the Numba, they are really robust. So they are investing a lot of money to provide like this easy way to convert a Python code in a C++ or a C. Sorry. So I think this make the library robust, and I think in R, the way that R managed with the parallelization, so sometimes it's different of the way that Python managed. So, but it's nice to compare. And one thing that I just want to show, the last. I didn't include because I like to idea to present these libraries, but here in the EU map, in the parallel, we have like one function that it's important, get this apply along X. So, and you can see this is actually like one of the best answers for a Stack Overflow question, and the code, it's really nice. We just change it and adapt it to put here. But this function, it will process an operation in a NumPy array in parallel. So you can, each of that pixel will be sent to a different core. So it's a kind of the same thing that you are saying in R. But this function, it's better to use like high level functions or applications. So for example, if you want to calculate a linear model over the temporal over a time series, probably this function is better, because I don't know if it's possible to do it in Numba, because Numba, it's more like for like this generic processing and statistics operation. But to process more, I don't know, some time series analysis, a breakpoint analysis, or things like that, probably you need to use like high level Python functions. And this is a good starting point. Just use a regular implementation of Python to process each pixel in parallel using all the cores available.
Yes, last week we spoke about the Q or Julia. So there are also functions in Julia programming language to also test the results for Vidal. So that would be a
yes. Using the same data set and the same hardware, yeah.
Hi, video. In video, this one. Okay. So the question in the Zoom was, when you use a standard Python library, they use MKL by default. Yeah, so it seems that the only case when you use Anaconda. It depends of the way that you set up your environment, actually. So here in the VirtualBox, we did the setup using our Docker and using Conda. So for example, you can see here in this is the EU map GitLab repository. And when you create like a Python, this is how we create this Docker, and you can see that with Conda, you can inform the BLAS implementation. And the BLAS, as I explained it, it's this C library with these mathematical operations to manage arrays. So here you can choose MKL or OpenBLAS. So if you are working on AMD CPU, probably no, for sure it's better use OpenBLAS. But if you have an Intel CPU, you can just install with Conda. and install directly the MKL. So it's the easiest way to set up, and specific for the setup of the training session, we already use it. We are using like MKL in all these libraries that I presented. Okay.